Have you ever wondered how your phone just unlocks by looking at your face? Well, that's AI in action. And the magic behind it is usually something called a convolutional neural network, or a CNN. Now, understanding how these things work isn't just cool, it's pretty much essential if you want to ace your next AI or machine learning exam. So think of this as your ultimate visual study guide.
All right, so here's the game plan. We're going to start with the absolute basics. What even is a CNN? Then we'll break down its core components piece by piece. After that, we'll check out two legendary architectures that you absolutely need to know. Then we'll get into how filters act as the eyes of the network, and to wrap it all up, we'll take a quick peek at what's next, networks that can actually remember sequences over time.
So, let's start with the big question. What exactly is a CNN? Well, at its heart, it's a machine that literally learns how to see. It takes a bunch of raw pixels and turns them into a confident prediction.
Okay, so here's the textbook definition. A convolutional neural network is a type of deep learning model that's built specifically for data that comes in a grid, like a picture. But here's its superpower. You don't have to tell it what to look for. It automatically learns to spot the important features, things like edges, textures, and shapes, all by itself.
This right here gives you a really clean, high-level view of the whole process. You start with your image, it goes through a convolutional layer to find some basic features. Then a pooling layer comes in to simplify things, making the data easier to handle. And finally, a dense layer makes the final call, which leads to the output. You can really think of it like a funnel, where the information gets more and more refined with every single step.
In this just illustrates that funnel effect perfectly. Look at how the input layer starts as a 36 by 36 block, right? After just one convolution, it's already shrunk down to 26 by 26. Then, after pooling, it's down to 12 by 12. See? Each step is reducing the physical size, but is actually pulling out more and more meaningful information. It's all about focusing the network on what really matters to make that final prediction.
Okay, so now that we've seen the big picture, let's pop the hood and really look at the essential parts that make a CNN tick. Trust me, these are the building blocks you are definitely going to be asked about on your exam.
So a typical CNN has 5 key stages. First up, you have the input layer. That's where the raw image data comes in. Second, the convolutional layer. This is the real workhorse that finds all the features. Third is an activation function, something like ReLU, which basically decides which signals get to move forward. Fourth, the pooling layer, which simplifies everything. And last but not least, the fully connected layer, which takes all that learned information and makes the final decision.
Let's just zoom in for a second on that activation function, specifically the rectified linear unit, or ReLU, as everyone calls it. The formula is crazy simple. It's just max of 0 and x. If you look at the graph, you can see if the input is negative, the output is 0. The signal just stops. If the input is positive, the output is just the input. The signal passes right through. This incredibly simple on-off switch had a massive, massive impact on deep learning.
So why is this little function such a game changer?
Well, first, it introduces nonlinearity. Without that, networks can only learn simple straight-line relationships. ReLU lets them learn all the complex curvy patterns you find in real-world images. It's also super fast to compute. And, this is crucial, it helps prevent the vanishing gradient problem. That's a huge issue where the learning signal gets weaker and weaker as it goes back through a deep network, until the first few layers just stop learning. ReLU keeps that signal strong, which means we can train much deeper, more powerful networks, way faster.
Okay, so we know the parts. Now let's see how they get put together in the real world. We're going to look at 2 landmark models that every student of deep learning really should know. An early pioneer and, well, a modern powerhouse.
This slide right here is your perfect exam summary. On the left, you've got LeNet 5 from way back in 1998, the pioneer. It used older tech like TAN activation and average pooling, and it was designed for a pretty simple task, reading handwritten numbers. Now, on the right, you've got ResNet from 2015, a modern titan. Its huge innovation was something called skip connections. It uses that efficient ReLU we just talked about, and it was built to crush massive complex datasets like ImageNet. The evolution between these two is just crystal clear.
And here it is, the LeNet 5 architecture. Just notice how straightforward and sequential it is. An image goes in, it hits a convolution, then a pool, then another convolution and another pool, before it gets to the final layers. It's a really simple, elegant design that was absolutely revolutionary for its time, and honestly, laid the groundwork for everything that came after. Now look at this. This is the heart and soul of ResNet, the residual block. So the input x goes through the normal layers, creating f of x. But And this is the genius part. The original input x also gets to skip all those layers and is added back in at the end. This skip connection basically creates an express lane for the gradient, which completely solves that vanishing gradient problem we mentioned. This is what allowed engineers to start building networks that are hundreds, even thousands of layers deep, something that was totally impossible before.
So, we've talked a lot about convolutional layers, but what is actually happening inside of them? The secret is something called filters, or you might hear them called kernels. The best way to think of these is like tiny, specialized little eyes, and each one is scanning the image looking for one very specific thing.
So what do these filters really do? Well, they're just small grids of numbers, little matrices. The network slides this matrix over every single part of the image, and at each spot, it does a quick calculation. If it gets a high score, that means the filter has found the exact feature it's looking for, like a vertical line, a specific color, or a certain texture.
Here's a classic example for you, a vertical edge detector. See the pattern? You've got negative numbers on the left and positive numbers on the right. So when this filter slides over an area of the image that goes from dark to light, that calculation produces a really high number. And the result? It effectively lights up all the vertical edges in the image so the network can see them.
Okay, how about this one? This is a sharpening filter. It's got that big positive number right in the middle surrounded by negative ones. What this does is it drastically boosts the value of the center pixel compared to all of its neighbors. That increases the contrast and makes all the details in the image just pop.
And on the flip side, you've got a Gaussian filter, which is for smoothing or blurring an image. It works by averaging out the nearby pixel values, but it gives a little more weight to the pixels closer to the center. This is a fantastic way to reduce any random noise in an image before the main feature detection starts. It just helps to clean up the signal.
So far, everything we've talked about shows how CNNs have mastered spatial data, like the pixels in an image. But what about sequential data? Things like a sentence of text, or maybe a time series of stock prices, where the order of the data is everything. For that, you need a totally different kind of network, one that has a memory.
And that brings us to recurrent neural networks, or RNNs. A basic RNN has this simple feedback loop so it can remember past information, but it really struggles with long sequences. It kind of has a short-term memory problem. The solution to that is the long short-term memory network, or LSTM. It uses a much more complex memory cell with these things called gates to solve that memory problem, which makes it excellent for understanding long-term patterns, like the connection between the first word and the last word in a really long paragraph.
This right here is the LSTM cell. Now, I know it looks complicated, but the core idea is actually pretty simple. Think of it like a smart memory system that has 3 gatekeepers. The forget gate decides what old information isn't relevant anymore and should be thrown out. The input gate decides what new information is important enough to be stored. And the output gate decides what part of the memory should be used to make the prediction right now. It's this careful management of information that is the key to its powerful long-term memory.
All right, let's wrap this all up with a quick cheat sheet for your exam. The absolute must-know points are these. CNNs use layers to learn features from grid-like data, like images. ReLU is the key activation function that makes modern deep learning actually work. ResNets skip connections were the breakthrough that let us build incredibly deep networks. And LSTMs use special gates to manage memory, making them perfect for sequential data. Got it?
Okay, I'll leave you with a final thought to chew on. We've just broken down how a network learns to see and understand what's inside an image. So if you flip that around, how would you even start to design a network that could do the opposite, one that could create a brand new image, just from a text description? That's where this whole field is heading. Good luck with your exams.